Okay, today we will take up to details of totally asymmetrical induction machine. Means we have asymmetry in both stator and rotor, and we typically take a wound rotor type of a configuration, and we took as a the most the simplest type of a configuration was one winding in stator and one winding in rotor. Okay. So, the system that we considered were as follows. Okay. So, we said that there will be a stator, there is a one winding, and rotor there is one winding, and we take it to be shorted. Okay. And this is rotating at omega r electrical radians per second, okay, and this is supplied by a voltage of frequency f. Okay. Then we said that this give rise to two fields plus omega and minus omega, is not it? And then that will induce a current in this, and this was the current induced would be what will be the frequency of currents? F minus Fr due to this, okay, and also another will be F plus Fr due to this, due to the, so one will be plus omega will give you minus Fr and minus omega will give you plus Fr. Is it okay? So, there will be currents induced in this winding, rotor winding of this. Okay. Now, what we are trying to say is, supposing I just write a table stator, rotor, we are saying that F will cause F plus or minus Fr, right, and what will be the F minus Fr will cause? You see, there is a current of F minus Fr which will rotating at omega r, right, and again this will give rise to two fields here with reference to rotor, okay, and the forward field will be in synchronism with the inducing field, just like in a normal induction motor. Okay. The one field, that is forward field, which is produced by the rotor currents will be synchronous with the inducing field, but there will be another backward field which will again give another frequency currents into the rotor. So, this may give rise to, from here this may give rise to F plus or minus 2 Fr. Okay. These currents. So, there again there are two currents, and both of these currents will give rise to two fields each, one forward, one backward, and the forward one will be in synchronism with the inducing field. Backward one field again will give rise to another currents in the stator. So, this is in the stator, and then this will give rise to F plus or minus 3 Fr, right. So, only the one is the fundamental is the only one which you are impressing, all others are induced, okay, because it is a shorted rotor. So, you know by the basic circuit theory, any other voltage induced for which the voltage source would be a short circuit, that you know, is not it? Any other voltage induced, your source will be taken as a short circuit. So, that will be a closed loop as far as the inducing is concerned. Okay. Then this will give rise to further f plus or minus 4 f r, right, and again it will this will lead to f plus or minus 5 f r. So, it continues. So, it may go, you can have f plus or minus k f r when k is even, and then in this case it will be f plus or minus k f r when k is odd. Okay. Now, you will have several frequency current induced in both stator and rotor. Okay. So, if you measure these currents, so currents will have several harmonic components. Okay. Now, this principle is very helpful because in practical cases there is always a possibility of asymmetry happening due to some accidents or the other, right. So, if you want to do a condition monitoring of a motor when it is in a large applications, rotor bar may get disconnected, stator there may be interturn faults, okay, or there may be some asymmetries. So, if you sense the currents, nowadays it is easy to have sensing possible through the sensors, proper sensors. So, you can, if you process the signals properly, okay, through a suitable processors. So, you may be able to identify those additional or spurious signals and which may be helpful in knowing the condition of the motor. So, this can be used for the so called condition monitoring of the motor. Is it clear? What is the importance of this principle or theory behind this? Because just like a doctor will know the condition of a patient if he has a heart problem. So, there will be spurious signal coming in the signal of the ECG. Okay. So, similarly this will be like an ECG for the motor. So, this is, so it is, if once you know there is some additional current other than F here, means something is wrong is happening in the rotor. Similarly, it is a cumulative effect of all these effects. Okay. So, in sum we can say that if you have one single phase winding in the stator, single rotor, this is what will happen. Of course, you can have several windings in stator, several winding in rotor. Okay. You can have a generalized concept. All this has come because of the basic concept of rotating field theory, that any winding current of a fixed frequency will give rise to counter rotating fields in the air gap. Okay. Now, so we did that. So, in the last lecture we have already said that this give rise to, if you apply a frequency f, it will give rise to different frequencies. Okay. Now, we try to write down an impedance of one winding. Okay. Now, how do you in a basic circuit theory, how do you define an impedance? How do you define an impedance? It will have its own resistance and reactance, that is what you will know. Any winding will have a resistance and reactance. How do you define reactance? Due to what? How do you define a reactance of a coil or a winding? Reactance come from what? Reactance come from inductance. How does inductance come? Inductance comes because of flux that it produces. If it was not producing any flux, there was no inductance. Okay. So, what we have done is, you have a resistance and we have the leakage flux, call it a leakage inductance, a leakage reactance. Then we have the harmonic fluxes, we always combine with this. This is what we did. Okay. So, we said that the self impedance, what is meant by self impedance? That means it is the voltage divided by current when no other windings are carrying a current. So, others are open. So, that means in this case when you say Z1, here your rotor current I2 is 0, it is open. See, when we took this first winding, that means what we are trying to say is what will be the impedance when the other winding is open. So, this is the Z1, which is nothing but whatever voltage you apply V1 divided by I1. I am telling you a very simple, sorry, that is what. Okay. So, V1 by I1 is the impedance of the single stator winding, which will consist of the resistance, leakage reactance, which contains all the harmonic leakages, and I split the mutual reactance component of this. This is the flux which also enters the rotor core. This X1F, X1B are due to the mutual flux. Okay. And what we did was, we said that if I call this coil and rotor is not carrying anything, we normally say, of course I am trying to do too much fundamental here, but anyway it is worth it. What we say is, this is the flux it produces, mutual flux, is not it, if it carries a current I1. Okay. It carries a current I1, it produces a flux, and this flux, when, because since this is AC, we only said that this flux will be a time varying flux phi, okay, which will typically vary with time like this, right. That means that you have almost, it is equivalent to just placing a magnet somewhere here, which will strength is changing. Then we said this flux, which will be passing through both the stator and rotor cores. Okay, if now you can say that X will be nothing but whatever the flux divided by current, that you call it as the inductance into number of turns, no doubt, into the omega you call it as the reactance. Okay, that is what we had done. Whatever this flux was produced, okay. Then what we did was, for our concept of rotating field theory, we said okay, this is equivalent to, okay, because what is this flux doing? Flux is inducing a voltage again in the winding, because of time by the Faraday's law d phi by dt. That is what this time varying flux is inducing a voltage into the in the winding. Okay. Now we said this is equivalent to, I will have two fluxes, phi forward and phi backward, both are equal, no doubt. So if you have 1 Weber as this, I said no, it is equal to half Weber this way, half Weber the other way. So the net effect will be same as pulsating, but you consider this to be, instead of pulsating flux, into a rotating flux. That is what we did. And what is this rotating flux doing? This is also giving you a voltage, say EF here, and this is giving you a voltage EB here, is not it, in the same winding, and EF and EB will be the same as the voltage that this flux will give you, right. And now this EF we call it as, this is associated with the reactance XF, and this you call it as associated with the reactance XB, is it okay, right. So we split it into two and we call it as XF at XP, that is the reactance due to the rotating fields, okay. So we call it as X1F and X1B. Some of them will be the total reactance X, right. So we can always say that this reactance of the coil can be represented by resistance, leakage reactance or X1 or something XL1 or whatever it is, then we say it is equivalent to XF and XP, okay, and this will be your total Z1, okay. Is it clear? If you have one winding, rotor open, so what I am doing is the basic circuit theory. Only we are trying to associate with rotating field theory, because pulsating flux in a core is equal to 2 rotating fluxes, clear. Okay. Now, therefore, R1 represents the resistive component and X1F X1B will be the self reactance due to forward and backward fields. Okay. Now, same thing you do for the second winding or rotor winding. Okay. For rotor winding, it will have its own resistance R2, leakage reactance X2 and X2F and X2B. Okay. So, what you are trying to do is, I have kept I have kept the rotor winding is carrying a current I2, okay, and it will have its own impedance here, and my stator is open. So, you can always say Z2 is whatever V2 by I2, okay. Is it clear? It's like another winding of a transformer. So, you can similarly have X2F X2B. So, X2F X2B will be the flux due to forward and backward produce the rotor currents, and it is natural to expect X2F will be proportional to N2 square and X2B also will be proportional to what is N2 is number of turns, rotor number of turns. So, it will proportional to the square, right. Again you are all aware of this. Okay. Okay, now we have already discussed how it produces F minus Fr and F plus Fr. We already discussed. A winding in a stator, if you put F, rotor will carry, forward field give you F minus Fr, backward will give you F plus Fr, right. So, that means if you put 50 cycles, right, if the rotor is rotating at a slip of 10%, you will have 45 cycles, sorry, it will have 5 cycles and 95 cycles or so, right. So, Fr of course is the electrical speed. So, we have already seen that that they will all go on continuous to produce forward and backward fields. Forward field will be stationary with reference to inducing field, forward will be stationary. So, it does not produce anything. When something is stationary, it will not induce anything, is not it. In the backward only it will go on creating a chain reaction. Okay. Then we discovered it will be F plus F, F plus R minus 2 Fr, F plus R minus 4 Fr, F K Fr in the stator winding. Okay. And similarly, we said it will be F plus R minus Fr, F plus R minus 3 Fr, F plus R K Fr, where K is odd in the rotor winding. Okay. Is it clear up to this point? How you will have a different currents induced, so when there is a asymmetry in stator and rotor. Okay. Now, we have to go back from field to circuit. So, if I apply a voltage V in the stator winding of frequency F, this is the frequency F, voltage equation for fundamental frequency F. Fundamental frequency F, you write a voltage equation because you are applying voltage V. So, it will be I1 into the Z1, okay. But if the rotor also will carry a current, rotor will be carrying two currents, one at frequency F minus Fr, another frequency F plus Fr, is not it. Rotor is carrying two currents, but that will also by mutual effects which will also induce a voltage in the stator winding, is not it. Since the rotor is carrying a current and producing its field, so it will be, and what is the voltage it will induce, which will be equal to the mutual reactance, which will be a product of X1F X2F, right. What is a mutual? Because you know the self and mutuals, if self inductance is L1 and L2, the mutual will be root of L1 into L2, isn't it? This is again basic circuit theory. Okay. So, this current I2 at F minus Fr in the rotor will induce a voltage of frequency F in the stator given by this. Okay. Now, this is again F plus Fr will also induce a voltage of frequency F in the stator. Okay. So, these are all the induced voltages due to the rotor. Okay. I hope this equation is clear, a simple equation, right. Now, go back to rotor. Rotor will have frequency f minus fr. For that I can write an equation, but for rotor is always short circuited. Short circuited means voltage is 0, that will be equal to its own impedance, that means its current into the impedance. Now, what I have done is, here you are referred to stator. I hope you know, you have always been referring all your equivalent circuit, you all are refer to stator by dividing the resistance by the slip. That is what you do. In normal induction motor theory, you have been referring means as if it is been brought back, you call it a transformation or whatever it is a rotor winding is as good as sitting on the stator. Okay. So, it will have the same. So, these are all referred to stator frequency, all of them, right. So, all you do simply is you are refer to stator frequency, all the reactances will be at the fundamental frequency, resistance is divided by that frequency. Okay. F over F minus Fr is your inverse of slip. Okay. Now, so rotor current I2 will induce a voltage in its own winding, the rotor winding, given by this x2f x2b. Then in the rotor the stator current I1, because which are the other one which are inducing in the same rotor winding of frequency f minus fr will be stator current F1, okay, and of course its own mutual reactance. F1 is first, and there is another stator current F minus 2 Fr, right, that will also induce a voltage. In fact, B and F is more symbolic, just to tell you whether it is due to a backward field or the forward field, otherwise the magnitude of XB and XF must be same, they are the same flux divided into half. Okay. X1f equal to X1b, X2f equal to X2b, okay, magnitude wise. Is it clear? F minus Fr. Okay. Now, you can, therefore, what you can do is you can write a general equation for this. For any stator frequency f plus or minus kfr, where this is the stator voltage equation. What is k here? Even or odd? K even, right. So, that will be this frequency f1 is the I1 into this and R1 into f by f1 plus leakage plus mutual, that is self reactance into its own current minus mutual due to the respective rotor currents, that will be whatever is F1 plus Fr and F1 minus Fr, right. The two frequencies will induce the frequency current F1, okay, and of course, this is the mutual reactance. So, we can write for any frequency, any stator frequency, and this will be 0 for all frequencies except f equal to fundamental, only except the first equation where it will be V, otherwise it is all 0. Okay. Is it clear up to this point? So, you can write down the voltage equation, because you have to write, because since all the frequencies are present, you write down the voltage equation all the frequencies, because the system performance will be a cumulative effect of all the effective frequencies. Okay. Then similarly, for rotor frequency F2 f plus or minus kfr by k is odd, again you can write a similar equation, F2 R2 by f by F2, then X2f X2b, then for to induce a frequency F2 in the rotor, there is a stator frequency, one is F2 minus Fr, another is F2 plus Fr. Well, there are again two frequency currents which will induce this frequency F2. So, you have this rotor frequency, where of course, you short it is 0. Okay. So, you have a general rotor equation. Okay. Is it clear? You have one general stator equation, general rotor equation for any frequency F1 and F2, right, which is given by F plus or minus k Fr, where one time k is odd, another time k is even. Okay. So, you can represent this by an equivalent circuit. Okay. Now, one is for the basic one, this is for the frequency F, isn't it? But all refer to stator, so it will look similar like a, it will look like a transformer equivalent circuit. Equivalent circuit is this will have R1, X1, X1F, X1B, okay, Z1, and mutual will be here it is X2F. Okay. So, this will be the current of F minus Fr, and this will be rotor current of F plus Fr, and you know this will be R2 by S and R2 by 2 minus S, right, and these currents will induce. So, the voltage equation will be due to this current I1F and another current I2F minus Fr and I2F plus Fr, okay. And then this will give rise to a stator frequency F minus 2 Fr, stator frequency, and again that is reflected by the resistive component being divided by 2s minus 1. So, now it is 2s minus 1, okay, and this is F2 F plus 2 Fr, that is 3 minus 2s, where s is the slip. Okay. Then you go on like this, right. So, it goes ad infinitum, and fortunately you will notice that the magnitude of the higher frequencies go on diminishing. Okay. In fact, you know, if S is equal to 0.5, what will be this frequency? It will be frequency is S is equal to 0.5, it will be DC. So, you will find something which is stationary also, okay, and this is called a George's phenomena. Sometimes they discovered if stator is asymmetrical, it will suddenly started running at half speed, right. So, a machine can run at half speed if there is a DC component in the stator. Okay, this is the equivalent circuit. Of course, I have done the measurements. In fact, you can do one of our generalized machine in the lab. You can do a harmonic analysis. You can harmonic spectrum. You will see all these frequencies are present. Okay. Okay. Now, what have you? Now, if I have 1 winding, now why not I have a generalized Mn winding? I have M stator windings and N rotor windings. Arbitrarily, they are displaced. Okay. So, the presence of asymmetry leads to frequencies F1 in stator and F2 in rotor. This is what we know, again it is repeated, no obvious. So, F1 equal to F plus or minus K1 Fr, where K1 is even, K2 Fr, K is odd. Okay. Now, voltage of frequency F1 are induced in stator winding by currents of F1 minus Fr and F1 plus Fr, and voltage frequency F2 induced in stator winding by rotor currents of frequency F2, no, actually this should be F2. Okay. Now, let us consider the general case. Let there be m windings in stator, m windings S1, S2, Sm in stator. Instead of 1 I have m winding, and I have n winding in the rotor R1, R2, Rn. Now, let S1 be the reference winding. Okay. So, what we are trying to say is, I have a machine, in the stator I have several windings, 1, S1, S2, S3, okay, and go to Sm, right. So, this is a very powerful tool in a way. You can have any number of windings in the stator, any number of turns in each, any number of any type of disposition. Okay. This angle will be, if this is S1 is reference, so you call this as theta S2, theta S3, whatever it is, of course in the proper direction, no doubt. Similarly, you can always have R1, R2, Rn or something, okay, N1, that is okay. So, we have this. Now, let the number of turns be Ks2, Ks3, Ksm with reference to S1 winding, and Kr1, Kr2, Krn with reference to S1 winding. So, they will have different number of turns. I hope there is no problem in understanding this, okay. And they are displaced also by different angles, okay. Theta S2 is the angle between S2 winding with all with reference to S1 winding. Theta S3 is S1 winding, this is some angle theta Sm from the S1 winding, and we can always say alpha is equal to e to the power of j theta, okay. Similarly, theta R2, theta R3, theta Rn for the rotor winding, axis of rotor winding will displaced by respective winding with reference to R1 winding. Do not go to S1 winding. Why? I have put because I have put S1, originally we took one winding only, one in stator, one in rotor, okay. So, S1 R1 we consider to be the reference for that purpose, okay. Because rotor winding, because rotor is rotating. So, if you say it refers to S1 winding, you will be in a real trouble, because it is rotating. So, it will be, it refers to omega t and other things will be there, okay. Now, when you have one winding, you can write one equation. If you mn winding, what you do? You must write m plus n equation for all the windings. Since it is too clumsy, you normally use the matrices, use the matrix method. So, you can always say my stator voltage equation Vs, then Rs plus jXs, and which will have reactance matrix, forward field Xf, and you can write for the backward field. Fortunately, just take the conjugate of this, that will be the backward field, okay, and that see due to frequency F1, this is the voltage equivalent frequency F1, right. Then it will, as we said, there is a mutual reactance matrix MSR, okay. This MS is the self reactance matrix, and we will see what it is anyway, into XF into IR into F minus FR, okay. Then another is MSR XP into F1 minus F. I think there is a mistake here. This has to be okay, this has to be MSR conjugate XB F1 by F into IR into F1 plus FR, right. Okay. So, you have MS here, MS conjugate here, MSR here, MSR conjugate here, whatever happens to forward and backward, okay. This will be a general equation. Then similarly for any frequency, this is Vs f by f1 we can write it as Rs f by f1, okay, where Rs Xs are stator resistance. So, it is the same thing. Is referred to the base frequency f. Right. Now, Ms Xf and Ms star Ms conjugate Xb are the stator mutual reactance matrices due to forward and backward fields. Okay. That means you forget about the rotor, but it is on several windings, there will be a mutual between S1 S2, that will also give rise to forward backward fields, its own voltage induction etc. Similarly, you have MSR XF and MSR conjugate XB are mutual reactance between stator and rotor due to forward and backward fields, right. So, there are forward and backward fields produced by each of these currents in the air gap. So, you cluster them into matrices. Okay. Now, what are these terms? If you understand this, maybe it will be, see MS, that is the self inductance coefficient matrix, we call it as, are the functions of winding turns and space displacements. This is more like a coefficient matrix. I think this is the point where you need to understand and introspect. As far as the 1 is concerned, there is no, it is the, so this will be relating to say S1, S2 going up to Sm, this also S1, S2 going up to Sm, is not it. So, first one will be same as Xf, no problem, because S1 is my reference winding, right. Then S1, S2, it will induce a voltage, we have already seen it is induce a voltage which will be Ks2 times, is not it, but it will not induce at the same time, it will also be phase displaced by alpha S2, where alpha S2 is e to the power of j theta S2, is not it. The forward field will induce a voltage which will be later in the second winding. Similarly, the M winding will have Ksm by alpha Sm. Okay. We have explained it earlier also. A forward field will go on inducing the voltages in the other windings proportional to the number of turns, but phase displaced by alpha, right. Okay. And similarly, S1, S2 will be the conjugate of this. So, if it one if the second winding to first winding the voltage will lag, second to one it will be leading by the same angles. So, so we can have this. Now, mutual between the second to second will be proportional to square of its own turns Ks2 square, and you can go on writing between S2 to Sm is Ksm Ks2 alpha S2 by alpha Sm etc. So, you can now with the same logic one you continue up to here, then last term will be Ksm square. So, the diagonal elements will not have any phase displacement because they are all self of its own windings, self of its own winding, right, S1, S2, Sm. Okay. Is it okay? It is due to forward and backward fields. Okay. Now, MSR, that is the between the stator and rotor winding will be between product of this. Okay. This will be the thing which will be the product of these two one Ks2 alpha S2 etc. and KR1 etc. Okay. This will be the MSR, right. Now, the rotor equation also you can write VR is equal to RR F by F2 JXR MR MR star XB IR F2, then MSR. Now, rotor equation, see MSR is the coefficient between the stator and rotor windings, which will be a function of its turns and the dispositions. Now, if the stator to rotor is MSR, then rotor state will be, it will be transpose and conjugate, okay. And so this will be the due to F2, it will be F2 plus Fr and F2 minus Fr, and this will be the term MSR transpose conjugate XF into IS, then it will be MSR transpose into XP into IS, okay. So, transpose and conjugates, you must understand the if the physical significance, both will be there, right. If the stator rotor is direct, another could be transpose, okay. Okay. Now, RR XR are of course the no problem, it is resistance and leakage reactances, and MR XF and MR star conjugate XB are the mutual reactance due to forward and backward fields. Rotor will have mutual reactance between forward and backward fields, okay. Now, this is called MSR transpose XF and MSR transpose conjugate XP are the mutual reactance matrices between the rotor and stator due to forward and backward fields. So, this is due to forward field, that means if the rotor carries a current, it will give a forward field, and that will whatever it will induce in the stator, that will be related with this, okay, and this is the backward.
So, why we are taking MSR transpose? So, for the forward, why we are taking MSR transpose?
No, MSR transpose XF, MSR, why we are getting MSR transpose? Because if it is stator to rotor is MSR, rotor to stator will be MSR transpose, okay. The other way around, okay. If you just look at some winding, because the transpose comes because they are not equal numbers of stator and rotor, okay. So, easy to write, MR is the coefficient matrix for the rotor self inductance, which will be proportional KR1 square, KR2 square, KRN square, and the between the stator R1 to R2 will be KR1 KR2 by alpha, this will be alpha R2 I think, okay. This will be alpha R2, this, and the last one will be KR MR will be KR1 KR2 alpha R2, then KR1 KRN alpha Rn, okay. So, we have a expression for all these coefficients. I know it is looks little messy at this point, and it requires calm, you sit and understand, right, these things, okay. Now, so in a normal generalized machine, so we now call it as a generalized machine of Mn windings, okay, where they only at Vs is the applied voltage to the stator windings, okay, and Vr is the induced voltage in the rotor winding, there will be 0, and Vs is also 0 for frequency other than the fundamental frequency f, okay. Okay. Now, we have messed it up, right. There is a mess in the stator and mess in the rotor. Let us try to see whether we can bring some order into our discussions now, okay, right. So, we will, because what you go out with some symmetry, in your mind. Okay. One is if there is symmetry, whether it will make us any better. Okay. Now, if they now one thing you know that if there is both symmetry in the stator winding, okay, asymmetry in there, it will lead to large number of equations, large number of frequencies. Now, if both are symmetrical, you are very, very happy. Normal induction motor, both are symmetrical. How many frequencies you have? In normal induction motor, 3 phase stator, 3 phase rotor, how many frequencies you are having? How many in stator? How many frequencies you have in stator? Only one, F only, 50 hertz only, you are happy, okay, not any other thing. How many in rotor? One only, slip frequency, right, you are very comfortable. But you have a problem if the supply voltage becomes unbalanced, then you have 2 frequencies in the rotor, okay. So long as supply is balanced, this is your no problem. But if any one of these becomes asymmetrical, if any one member is symmetrical, then the frequencies get drastically reduced, even if one is symmetrical, okay. And that is what if the rotor is symmetrical, then the stator field induce balanced polyphase currents in the rotor. So, what happens is if the rotor is symmetrical, the forward field will give rise to very balanced currents in the rotor. So, balanced currents in the rotor means it will only give rise to forward field, which is in synchronous with the inducing field, okay. Even if there is a backward field in the air gap, it will give rise to a negative sequence currents, and which in turn will give rise to another backward field which will be in synchronism with the inducing field. So, there is no other additional field which will start creating another induction of currents in the rotor, in the stator, right. So, there is no further induction. So, forward field produces positive phase sequence and backward with negative phase sequence, okay. So, we know the balanced currents in the symmetrical rotor will produce no backward field, okay. So, further induction of currents in the stator will not be there, is it okay? There is no further induction of currents in the rotor, okay. Right. Now, lastly I will close with this. Supposing your stator is symmetry, rotor is asymmetry, okay. Okay, now symmetry and balanced. So, it will give rise to only forward field. If stator is symmetrical, it gives rise to forward field, but rotor is asymmetrical. So, what will happen is it will give rise to unbalanced rotor currents, okay, which will give rise to forward and backward fields, okay. Then there will be no backward field due to stator currents, okay. Stator is symmetrical, only forward field, but rotor is asymmetrical, it will give rise to forward and backward field, and the backward field of that due to asymmetry in the rotor, stator forward field produces unbalanced currents in the of F minus Fr, okay, which will produce forward and backward fields, and forward field of rotor is synchronous with the inducing field, there is no problem. The forward field of rotor is synchronous with the inducing field, but the backward field of the rotor will induce a frequency F minus 2 Fr in the stator, it will induce a F minus 2 Fr in the stator, but fortunately stator is symmetrical and it will not produce any more fields back into the rotor. So, there will be F here, F minus Fr here, and then F minus 2 Fr, and then it will stop, right. So, there is no further induction of currents in the rotor beyond this, okay. Of course, if right. So, this is with this little happy note we close here. So, tomorrow in next class we will take up how we write down the equations for this and how we can get the symmetry into the things, okay.